Voilà, on a le plaisir d'avoir Sofia FLORES, qui vient de l'Institut d'astrophysique de Paris. Et donc, c'est un peu intermédiaire entre mécanique statistique et astrophysique, je dirais. Donc, on a changé de titre, il n'y a pas le 2. Donc, on repart au 1, je suppose.
So hello, thank you for being here. I'm Sofia FLORES. I'm a third-year PhD student working at the Institut d'Astrophysique de Paris with Jean-Baptiste Coury. And during my PhD, I've been interested in applying statistical field theoretic methods to stellar dynamics. That means to gravitational and body problems. And because you're not astrophysicists, I will try to focus on the techniques that I've employed and on my main results, and I will try to keep the astrophysics introduction very short. So let me start by doing this. The system that I'm interested in is our galactic center. So in our galaxy, in the Milky Way, we can find a cluster of stars that follow a very rich dynamical behavior. So these stars are orbiting the supermassive black hole Sagittarius A star, and they will diffuse in their orbital parameters. So they will diffuse in their orbital plane orientation, in their eccentricity, that means the shape of the orbit, and in their semi-major axis, and that means the size of the orbit. And in my work, I've been interested in the process of diffusion in orientation, which is called Vector Resonant Relaxation. Okay, so let me introduce the Hamiltonian description of vector resonant relaxation. What is interesting about the galactic center is that timescales are very hierarchical. So we're able to average over the short-term evolution. For example, here I will perform a first average over the orbital motion of the star. So here is the orbital plane. This is a point star, and then by averaging over the orbital motion, I get an ellipse. And then by averaging again over the in-plane precession angles, I get an annuli. So in the vector resonant relaxation, each star is represented by a disk of mass, semi-major axis, and eccentricity constant. And the only dynamical quantity, the only time evolving quantity is each star's orbital plane orientation. So we can track this orientation by following this point on the unit sphere. And if I now want to consider the full number of stars of my system, the system will resemble something like this. So here, each point on the sphere corresponds to the instantaneous orbital plane orientation of a star. So even if you're not interested about astrophysics, this is the system that I'm looking at. So it's a statistical physics problem. And you can see that this system is isotropic. It is also time stationary, and it is highly correlated. You can see this vortex-like structures appearing and disappearing. So is the statistics of the system that I'm interested in. So how do I do this? Well, I will first start by introducing the empirical distribution function of the system. So this is the discrete distribution function, where L here is the angular momentum of a star, and H is the Hamiltonian of the system. And this distribution function characterizes the state of the system at any time t, and it evolves according to the Klementovich equation for this discrete distribution function. So here the brackets are the Poisson brackets. And since the problem is spherically symmetric, I will expand the distribution function over the spherical harmonics. So I will track the evolution of the system by looking at this FLN of t. Right, so I will now introduce some a more compact notation. So I will call Lm the spherical harmonics number, t will be time, and in the case of isotropic VRR, Lm, that means the unit sphere, is exactly phase space for this system. So from the evolution of the discrete distribution function, I can find an evolution equation for this distribution function f. So you can see that it follows exactly a nonlinear evolution equation. So I only have a nonlinear term here. I've implied the summation of repeated indices, and this gamma coefficient here is a coupling coefficient that was coupled scales 1, 2, and 3 together. So this coupling coefficient is classical, and it is entirely determined.
So to make sure that I understand the system correctly, so are you thinking of stars orbiting around the galactic center, or is it something else? Because you said you average over 10 years, but wouldn't the orbital period much longer than 10 years?
Yes, so this is for a star. This number is for S2, which is very close to the supermassive black hole. So this this timescale will change for stars that are further away, but the hierarchy is still verified. So what I'm interested in is the fact that over this effect, the diffusion in orbital plane orientation, I can average over this space. So it's the hierarchy that I'm interested in, right? Right. So as I said, this coupling coefficient is entirely determined by the equations of motion. So it encapsulates the microscopic description of the dynamics. And well, this coupling coefficient is local in time. So here, actually, this equation is local in time. So this F1, F2, F3 will be evaluated at the same time. And then there will be some very complicated expression that encapsulate the description of the interaction. And for reasons that will become clear later on, I will call this coupling coefficient the bare interaction vertex.
Yes, I have a question on the same spirit. So is this for stars which orbit a supermassive object at the center, or could it also apply to self-gravitating globular cluster?
So for globular clusters, there is this. So this process also occurs in globular clusters. Maybe the orbit averaging won't be exactly the same, but I mean in a globular cluster you can find this diffusion orbital plane orientation.
So you can find?
You can find this type of.
Okay.
So this is not limited only to the galactic system. Yeah.
Another question: is there an assumption that the annuli describing each star over this one is the same?
Yes. So that's a good point. Here I've assumed a single population system, so all stars have the same norm of the angular momentum. So that's why all the stars are on the same units here. Okay. Right. Right. So now I have the nonlinear evolution equation for my distribution function that characterizes the state of the system. And the point that I want to emphasize now is that the dynamics are strongly nonlinear. You can see that I don't have a linear term here. And therefore, I'm in the non-perturbative regime. There is no small parameter. So that's why the problem is difficult. And if I now want to take a step back and look at the previous equation, I could maybe add a linear term and a stochastic external noise. And this equation here could be described as Laplace equation, describing self-gravitating system and plasma. So for example, this linear term here will encapsulate phase mixing. This equation can also encapsulate the evolution of large-scale cosmological structures and even some stochastic growth processes like the KPZ equation. So this writing is very general, and all the specificities about the system, about the interaction, are hidden in this generic kernels. But in VRR, I'm only interested in fully nonlinear regime. So in my work, my goal is to characterize correlation functions of the system. And you may be familiar with the closure problem. So that means that when I take a two-point correlation function, for example, so C12, which is equal to ensemble average of F1, F2. And when I take the evolution equation for F, I find that the evolution equation for the two-point correlation function depends on the three-point function. So this means that the cumulants of the system follow a hierarchy that is not closed. And in order to be able to have a prediction for these correlation functions, I have to overcome the closure problem. here I want to also emphasize that when I mean ensemble average, I mean the average over the ensemble of initial conditions.
Maybe I missed the point. So in the previous slide, you wrote Boltzmann equations and a nonlinear term. What's the rationale for this equation? Like, is this a way to model your system, or is there physical reason why you only consider this nonlinear term, not the higher order terms?
So this equation is exact, and this is given by the dynamics of the system. So the dynamics of this process are exactly nonlinear. Here I have not neglected anything. And that's why this problem is very degenerate, because it's fully nonlinear dynamics. And what I was saying is that this equation is deterministic, and the noise comes only through the generation of initial conditions. So from my given realization of an initial condition, my field F will follow a deterministic path. So when I write this ensemble average, I'm averaging over the set of initial conditions. So, so yes, I'm taking the initial, I will talk about that later on, but the initial conditions will have a Gaussian PDF. Right, so the entire goal of my work is to overcome this closure problem in the fully nonlinear regime. And maybe if you're a cosmologist, I just want to stress that L for me will be K for you, and I also want to stress that this is the 2.2 time correlation function. So it is different from the power spectra where it's 2.1 time. Here is 2.2 times, so I'm allowing my correlation functions to have temporal depth. Right, so the methodology that I implemented is the Martin-Siggia-Rose formalism. Maybe you're familiar with this. And during the upcoming slides, I will try to take you through the main steps and the main ideas of this formalism. So the key point here is to have a path integral representation of this stochastic dynamic. Here I have taken the previous equation and I've explicitly written the noise that is generated in the initial conditions. So I'm taking my deterministic equation and I'm adding the noise coming from the initial conditions. So this looks like a Langevin equation, but you have to be careful here because I'm only injecting the noise at t equals 0. Then the next step is to represent the constraint on the dynamics of F. So I'm not going to look at any F, I'm going to look at an F that is a solution of this equation. So the probability distribution of the trajectories of the field follows from the ensemble, from the average over the noise. And here I explicitly reading the constraint on the dynamics, where F eta is a solution of this equation here for a given realization of the noise. And the key to MSR is to introduce an auxiliary response field. So the way this response field appears, this conjugate field appears, is by enforcing the dynamics, the constraint on the dynamics of F. So basically, I will write my constraint on F, and I want to set this constraint equal to 0. So basically, the trick that is done in MSR is to use the Fourier representation of the functional delta, where here my conjugate variable will now be a field. So this is how this F hat naturally appears, and if I now want to enforce to rewrite my previous equation, well, now I have an integral over this auxiliary response field F hat. Right? So the next step of this formalism is to integrate out the noise. So for isotropic VRR, yeah, my noise is Gaussian. So this thing here is a Gaussian PDF. And basically what I can do is to integrate out the noise and collect the different terms so that I can write the action. So basically I'm killing the integral over the noise, I'm collecting the different terms, and I'm writing this action here. Well, the first term is a constraint on the dynamics. So this thing here could be seen as the Lagrange multiplier of the thing, or this could be seen as a Lagrangian that allows me to recover the correct equations of motion for my field F. And then there will be another part, which I call S noise, which will capture the information about the PDF of the noise. So basically, if this PDF is, so if here I have exponential and a quadratic term in eta, this term here will be quadratic in f hat. So if it's quadratic in eta, it will be quadratic in f hat. So I still recover the information about the noise so that I can write p of f as exponential minus f. So this is the most familiar writing for you, I believe. And then, since I'm interested in correlation functions, the key is to introduce a partition function. So basically what I want is to have a functional that when I take derivatives of it, I recover the moments of f and f hat. So here j and j hat are just some sources probing the system. And here I'm ensemble averaging over this quantity here. And by knowing p of f, I can explicitly write what this means. So what this is doing, exponential minus s, is selecting the authorized path for f and f hat. And the second term here, we generate the moments of f and f hat. So if I now write the cumulative generative function, which allows me to recover the disconnected part of the moment, well, you can see that the 2-point correlation function is exactly the second derivative of this thing. And now I can introduce another quantity, which I call the response function, which will be average of f. So the key to MSR is when I'm introducing this response field is not only a mathematical trick, but it has a physical meaning. So this f hat allows me to recover the mean response function of the system. So basically, the correlation functions will tell us how the different fluctuations correlate at different scales. And the response function will tell us how the system will respond to an infinitesimal kick. So these two functions give out different insights about the system, but for systems that are thermal equilibrium, this correlation and response are actually proportional to each other. So isotropic VRR is an equilibrium, so considering correlation and response is the same thing. So as I said, in MSR, the key is to consider both correlation and response function. Basically, I want to simultaneously track the evolution of the 2-point response function and the 2-point correlation function. And the way I do this is by introducing a 2-point propagator. So basically, I'm just putting in the same thing, C and R. And if you remember the closure problem, we saw that the evolution of the 2-point correlation function depends on 3-point quantities. So for that purpose, I will introduce a 3-point propagator, which will encapsulate 3-point correlation functions and some other complicated things, so that I can write the evolution equation for G as this thing. So basically, I have the evolution of the 2-point propagator, which directly depends on the 3-point propagator. So here, I still have the closure problem. I haven't solved the closure problem because I still have 2-point quantities that depend on 3-point quantities, right? So the key to MSR is to introduce what is called a renormalized vertex. Basically, this vertex will allow the dressing of this coupling coefficient that is given by the dynamics of my system. So the way I introduce this renormalized vertex is by stating that I can decompose the 3-point correlation function or the 3-point propagator as a product of 2-point function in this new thing, which we don't know, which is the renormalized vertex. Right? So here, the introduction of the renormalized vertex is allowing me to rewrite this equation in a different way, where here I have introduced sigma, which can be viewed as a self-energy, maybe if you're familiar with that, and which, well, depends on the bare vertex, the 2-point propagators, and the renormalized. So introducing this renormalized vertex here allows me to rewrite my previous equation as a Dyson equation. And here I encapsulate the time derivative in the bare propagator. But you may have anticipated that here I still have the closure problem. So I still have a 2-point quantity that is a function of a 3-point one. So I still have the closure problem, and this slide, even though it looks a bit complicated, it's just a different rewriting of my original equations. Basically, what I'm doing here is I'm shifting the target of the closure. Instead of looking at 3-point correlation functions, I'm going to be looking at the 3-point vertex. Okay. So you may have anticipated, since I'm talking about Dyson equations, it would be very convenient to have a diagrammatic representation of my equation. So here I remind that the two-point propagator encapsulates the 2-point correlation function and the 2-point response function. This is the Dyson equation that I previously introduced. And by choosing this diagrammatic representation, I can rewrite this equation as this. So the trace propagator will be double line, bear propagator will be this thing, and this will be the self-energy sigma. So here, where there is a connected double line, I want to emphasize that I'm summing over space, and time. So this contraction here is actually very expensive. And as I said before, here I still have a closure problem. I still don't know what this thing is, right? So if I don't know what this thing is, I cannot solve the equation for J. So the idea of MSR is to approximate this renormalized vertex gamma so that I can have a prediction for my 2-point correlation functions. So the first simplest approximation one could do is to set the renormalized vertex to be the bare vertex, right? So here I'm just equating the renormalized vertex to the bare one, and this allows me to recover an analytical prediction for my 2-point correlation functions. And I can solve this differential equation numerically, and this is what I'm showing here. So this is a plot of the isotropic 2-point correlation function as a function of time for different scales, L equals 2, 3, and 4. So basically, I'm looking at a vortex of size L here. The full line corresponds to the n-body measurement of this correlation function. So what I'm doing is that I'm running n-body simulations, I'm ensemble averaging the simulations, and I'm measuring these correlation functions. And the dashed line corresponds to the bare prediction that I obtained from this theory. And the physical information you can get from this plot is what I call the vortex lifetime. So basically, if I'm looking at a vortex of size L, this time scale here will tell us for how long this structure remains coherent. And what you can see, what you can see is that the bare prediction does seem to recover the behavior of the n-body measurement, but it does underestimate it. So the idea is to go to next order in this scheme, and the next order accounts for considering the one-loop correction to this renormalized vertex. So at bare order, I just kill this thing, and at one-loop order, I will consider the self-consistent expression, the self-consistent dressing for this renormalized vertex gap. So now the MSR closure equations take up this form. This is my previous Dyson equation, and since the expression for gamma is self-consistent, I now have a self-consistent coupled equation, set of coupled equations. What I mean by this is that I have a Dyson equation which depends on itself and gamma, and I have a loop expansion for gamma which depends on itself and on the propagator. So the way I approach this problem is by doing a direct numerical implementation of this set of equations via a fixed point search. So what I'm doing here is I'm choosing a starting point for this scheme. I will just, for example, for gamma 0, I will choose the bare vertex, and for G0, I will choose a Gaussian correlation, and then I will update this equation, update the expression for gamma, and I will get a new set of gamma G, and I will repeat this procedure until I arrive to a fixed point. Yes.
And so for gamma, you have 2 times and 4 space variables.
So that's my next point. For gamma, I'm actually optimizing over 4 million parameters per iteration. And where does this come from is that in this scheme, I'm solving for every scale for every time at each step of the iteration. So basically, I have gamma, which depends on 3L and through M and 3, and it will also depend on 3 times. So why is this so extensive? Is because at each step of the iteration, I'm solving entirely this gamma here. And
you cannot remove one time if it's stationary?
so yes. So if in practice, what I did is I enforced stationarity. So I could only look at 2 times, and I also enforced isotropy. So I could get rid of this M dependence here. So even though taking into account all of these simplifications, this is still very numerically expensive. And the way so expensive is because I'm solving over the entire depth in time. Okay.
When you have sort of a loop, what does it mean? Does it mean that you are summing overall L?
Yes, exactly. So here, so the interest of having these diagrams is not to have to write the equations explicitly, but you're right. Here, I'm contracting over each double line. I'm contracting over 2 times, over 2 L's, and etc. So the sum, the numerical complexity comes from the evaluation of this.
Yeah. So it's an infinite sum overall.
Yes. So in practice, I do truncate this sum. I do truncate in L. But yes, in theory, this will be an infinite sum.
And how does the result depend on when you truncate?
This is something that I've explored. The system that I'm looking at, I'm only allowing a L equals 2 interaction. So basically, in the coupling, I'm only authorizing L equals 2. So given this thing here, for a given L, well, a given L will interact with L plus minus 1 and 2. So if I look at low L, I don't have to go that deep in the cutoff. So I can have a low cutoff and have these predictions be independent of that. And that's because I've restricted myself to a quadripolar. As I was saying, each step of interaction is very expensive, and all this iterative scheme actually took 25 days on a cluster. So it is very, very expensive. Yeah.
And so the way you look for the fixed point and for the solution is to iterate
Yes.
the same equation, etc.
Exactly.
You don't look like some a software to look for a fixed point by some
Yes.
I don't know, Newton method or something like.
So I would say that this iterative scheme is the most direct and robust way to look for this fixed point. I don't think it's the most optimized way. And the reason for this is since this type of formalisms haven't been applied for stellar dynamics, I wanted to have the most direct and robust way possible to look for this fixed point. So basically, what I've done is I'm looking at gamma and at the propagator. I'm starting from an initial, from a starting point. The fixed point is here, and basically, I'm just reaching that fixed point. But one thing one could explore, for example, is maybe I could look at this direction here, and then go down, do this, go down, etc. So there are some variations of this thing, but for now, what I've done is this direct numerical implementation. But what I've shown in my work is that this fixed point does exist. So this will allow me to look for more efficient ways to look for it. But the important thing is that I've shown that this fixed point exists. Right? So this is the renormalization procedure I was talking about. I remind that the 2-point propagator encapsulates the 2-point correlation function. So here I have plotted the 2-point correlation function for at each step of the iteration. And what you can see here is that, well, I started with a Gaussian initial condition for my correlation, and I plotted the output of the iteration at each step. And you can see that it does reach a fixed point, and this fixed point corresponds to the solution given by this order of approximation. So this is what I'm showing here. This is the same plot as before, where I've added the one loop prediction of the MSR scheme, and what you can see is that the prediction is significantly improved over the bare one. So it is the self-consistent dressing of gamma that provides accurate predictions for the correlation function. But what if we turn off self-consistency? That means, what if I consider this expansion here? In this expansion, I've killed the self-consistency in gamma, and I've considered bare vertices in the one-loop expansion. I think for cosmology, this corresponds to 1 pi, maybe, I don't know. But basically, I'm only authorizing bare vertices and dressed propagator. And what I've obtained by looking at this expansion is that this one-loop naive expansion, which corresponds to this one, does diverge a long time scale. So it's the self-consistency of gamma that ensures convergent prediction. So this is the correct expansion, and if you remember my iterative scheme, I not only get a prediction, I'm not only looking for G, but I'm also looking for gamma. So my scheme also allows me to recover a prediction for the 3-point vertex. So this is what I'm showing here. So not much is happening in this plot. This is my renormalized vertex gamma, which depends on 3 scales and 3 times. So a given triplet of L's corresponds to choosing one triangle on the sphere. So here I have plotted the amplitude of gamma for 6 different triangles. So each panel corresponds to one choice of L1, L2, L3. And I've measured the amplitude of this thing over the T2, T3 plane. So basically, I'm killing one of the times, and I'm just measuring the amplitude of gamma over one section of time. This is at bare order. Well, this is what we expect. Nothing much is happening since I'm just setting the renormalized vertex to be the bare vertex. And if you remember my previous slides, I told you that little gamma is local in time. So actually, it only has a chance to be non-zero, where T2 equals T3 equals 0. And given some significant exclusions on triangles on gamma, only 2 out of 6 triangles present show a non-zero value for this bare vertex. And what happens when I go to next order is that the previous triangles, for which I had an exactly vanishing bare coupling, now light up. So this is the same plot as before. It's the same way of measuring its amplitude. And what you can see is for the 2 triangles where the bare vertex had a non-zero amplitude, the renormalized vertex stays very close to it. But for the triangles for which the bare vertex is exactly vanishing, I do have some kind of structure for gamma. So this is the magic when I turn on self-consistency and I allow gamma to get dressed. I allow the interaction to get dressed. And there are some interesting properties of this plot. So first is the local dressing. That means that gamma would only light up for a localized region on the time plane. Also, you may notice that gamma only lights up for T2 greater than T3. That's because I have some causality constraints to verify. That means that when I'm taking into account this one loop contribution, there are some response functions that are intervening. Response functions are causal, so that's why only the upper half of the plot lights up. And I have another characteristic, which is the amplitude. So I would say that this is the most important characteristic to understand, is that even though gamma will light up, it would remain small in amplitude. So basically, I'm allowing for deviations away from the bare dynamics, but these deviations remain small. And it's this self-consistent dressing that allows me to reach and approach this fixed point. And if you remember my slide on MSR, the way I introduced this renormalized vertex gamma is by expressing the 3-point propagator as 2-point functions and the renormalized vertex. So now I show you a prediction for G, I showed you a prediction for gamma, so now I can get a prediction for this 3-point correlation. So this is what I'm showing here. This is the normalized 3-point correlation function. I've normalized it by the initial conditions for the 2-point correlation function. So it is a dimensionless quantity. The 3-point correlation function depends on 3 scales and 3 times, just as gamma. So here I've shown the prediction for the 3-point correlation function for 6 different triangles, and I've measured the altitude on the T2, T3 plane. And what you can see here is that at bare order, the same triangles that showed a non-zero bare vertex present a non-zero 3-point correlation function. And not only that, this 3-point correlation function is big. That means that non-Gaussianities at this scale are large. The triangles are presented an exactly vanishing bare vertex present a 0 3-point correlation function. And what happens when I light up when I allow the dressing of gamma is this, what you can see here. You can see that the same triangles that presented a 0 3-point correlation function at bare order now present a non-zero 3-point correlation function. So basically what this scheme is doing, as I take into account self-consistent loop interactions, is that I'm allowing for non-Gaussianities to appear. So I am allowing for the dressing of non-Gaussianities in my system. And what you can see is that even though these triangles light up, the amplitude of the squeeness of for these triangles remains small. So in the same way, I'm deviating away from the bare prediction, but I'm doing so, I'm only allowing for small deviations. And in the same way that in my previous slide, I show you an n-body prediction for the 2-point correlation function. I can also do so for 3-point correlation function. So I can go to my n-body simulations and measure a 3-point function. And this is what I do here. So here you see for this specific triangle, you see a vanishing bare prediction, a one-loop prediction that is non-vanishing. And what you can see is that the one-loop prediction does seem to recover the behavior of the n-body. So this is a success of the one-loop MSR closure for gravitational dynamics. Here I'm showing you some other triangles, and what you can see is that the one-loop prediction systematically reproduces the n-body measurement. Right? So maybe to summarize, I wanted to tell you about the successes and limitations of MSR. So first, the reason that we statistical physics are interested in correlation functions is because it allows us to characterize the dynamics of the system. So, for example, the 2-point correlation function gave us the lifetimes for the vortices that we see, and also the 3-point correlation function provides a direct measure of the system non-Gaussianity. The reason that I'm interested in vector resonant relaxation is because it can be seen as an archetype of fully nonlinear dynamics. That means that this equation here is very generic, and all the specificities about VRR are hidden in this kernel. So when I wrote my equation, I never had to specify the properties of this gamma here. And so the way I see VRR is I see it as a playground to test these statistical formalisms in the context of n-body gravitational problems. And what I've shown in my work is that this field theoretic method that MSR can produce the accurate behavior of fully nonlinear dynamics fully nonlinear gravitational dynamics. And what I've done is I've taken a generic framework and I've developed a generic numerical scheme to solve this equation. And I've hidden all the specificities about VRR in the starting point for this iterative fixed point scheme. So this is generic, but the specificities are hidden in the starting point. And the strong limitations of MSR are actually its numerical complexity. To give you an idea, the bear prediction took a few minutes on a cluster. The water prediction took 25 days, and if I were to consider tulip prediction, this will take 1 million years. So it's, of course, numerically beyond any reach. So what I'm looking into right now is to go beyond MSR and to look at a related path integral formalism, which is the functional renormalization group, applied to this gravitational dynamics. And I'm also looking to go beyond VRR by studying the more generic Poisson regime. That means that I want to consider a linear term and an external stochastic noise. And what I'm currently working on right now is in the process of phase-space turbulence. So basically, if I start with an anisotropic initial condition for VRR, you can see some phase mixing, what we call, and is this stretching and filaments that are forming. So I'm actually working on computing the power spectra for this. And I have 2 publications about this work, and if you're interested, thank you.
So at some point you were saying the 3-point vertex or correlation is not so much different. I mean, there are places where it was 0 and now it's not 0, but the amplitude is not so large. So naively, so there would be some up that so the system is not so far from a naive bare guess. So here the difficulty is that you are trying to find some fixed point, as you explained. Probably there are other expansion schemes where you would not look for a fixed point, but just do the bare computation, so explicit expression. But so you said the first step doesn't work that way, but you could go to maybe higher loops in explicit expression. Would it work?
You mean this type of expansion? Or
Yeah.
So this type of expansion, I say in this non-perturbative regime will not work. That is because naively we cannot, since little gamma is not a small parameter, we cannot expand in this little gamma. What the self-consistency is doing is allowing for the correct way of resumming. So basically, if you see this scheme here, I could technically express gamma IGI as a function of gamma 0 T0. So if I do this, I will have some higher order loops that only involve the bare vertex and the bare propagator. But the difference here with this expansion is I'm considering the bare vertex, but the dress propagator. So it's not exactly the same thing. So I expect that this expansion, the expansion in the bare vertex will inevitably blow up.
So as you're saying that the agreement for small times is a bit of a fluke, or I mean, it's not supposed to work as an expansion, unjustified.
So you mean why does it work?
Yeah, at some point. I mean, commenting on this point, I would expect that adding the next loop, maybe it works for some longer time. I don't know.
Actually, I would expect that considering a 2-loop would worsen the divergence.
Worse.
I will consider it will work less correctly, and I think the reason that for this time scale the prediction seems to be accurate, I think it's because the bare prediction is not that far from the correct answer actually. So the key point here is that I'm initializing my fixed point search in a starting point that is not that far away from the actual fixed point. Yes.
So you mean in this global framework, there's no cheaper, faster expansion scheme that would avoid the fixed point computation?
That will avoid the fixed point computation? Well, maybe in some regime, maybe in a regime where you have a linear term in your, I'm trying to look for it. So in the regime where I do have, for example, a linear term, I can't compute a small parameter. And if I do have a small parameter, then I'm in the perturbative regime. So that would be easier. The reason that it's so hard for VRR is because I don't have a small parameter. So the dressing has to be self-consistent in some way.
Related to this issue of adding higher orders, how is it possible to estimate how much one would gain in accuracy by adding this two-loop self-consistent thing that takes 1 mega a year?
So I would expect the corrections to be small in the sense that the one-loop prediction is itself pretty good. So I would expect for it to be a minor change, and in any way, I mean, the tool of order prediction is beyond feasible.
Yeah,
but I would expect not to be.
And so at the end, so you said you are now working on different initial conditions. You said anisotropic, if I understood it correctly.
Yeah.
So it means you are using the same framework, but now you don't have isotropy, the isotropy assumption anymore.
So I'm not using MSR for this project. I'm actually using something else because here I'm only interested. For now, I'm interested in the power spectrum. So just 2 points same time. So the entire difficulty of MSR is that I'm looking at time correlation. So here I'm using another framework that allows to predict the slope of the power spectrum. But if I were to consider an isotropic initial condition for VRR, this will actually add a linear term to my equation. So basically, if I consider, I can write F equals mean F to delta F. If I now consider the evolution for this delta F, I will have something like this: delta F to gamma delta F squared. So by having a non-zero mean field, I'm adding a linear term to my equation. So this. And I insist the reason why this problem is so hard is because I don't have.
Just one naive question. So if I understand correctly, at least for your problem, you're saying that this three-point vertex is fully characterizing nonlinear dynamics. And you compare the numerical embodied simulations and this one-loop predictions. But when you do that embodied simulation, are you also accounting for interaction between stars, or is it only between central supermassive black hole and the stars?
So the interaction is only for the stars. So the Hamiltonian of the system is written for the n stars of my system, and it is sensitive to Li.Lg. So the supermassive black hole is what allows me to average over this time scale. So basically, it's what will source for some stars the percenter precession angle. But for this problem here, the interaction is only between stars. So the n stars are talking to everybody at the same time. It's long range.
And the other question is, like, if I do the same analysis for other parameters, for example, eccentricity or inclination, do I get to see the same set of equations, or do I have to modify things here in order to?
Do you mean for this process here, is it still nonlinear?
Right. So if I say I'm interested in diffusion of eccentricities or inclinations or other orbital parameters, is it going to be similar or?
So I'm guessing for eccentricity, at least you do have a diffusion coefficient. I mean, you do have some sense of linearity. I think the true degenerate problem is this process here. So this free process could be seen as uncorrelated in the sense that for the timescales that I'm considering, well, I can consider that eccentricity is a major constant. But Jean-Baptiste with another student have looked into the diffusion in eccentricity, but not with this type of formalism.
curiosity, is there like a regime where you can the self-consistent method is correct? Kind of like how we arises in the large N approximation.
Is there a rigid?
Like how usually like mean field arises when you consider like large N models like that, and is there like an analog like where this closure, this self-consistent equation arises when you introduce like an extra fictitious parameters, like considering high-dimensional spheres or something like that?
The mean field for isotropic VRR is 0. It would be just taken n to infinity. You're just coloring all the sphere with the same. Maybe what you had in mind, I don't know if that answers your question, but so there is a this one. So the Vector formalism provides an exact expansion for gamma. So it's this term here, and basically is this derivatives that will generate the 1 loop, 2 loop expansions. So this equation is exact. What I'm doing is truncating the derivatives that appear here. Yes. But I mean, we do have an exact expansion for gamma, but I don't know if that is related to your question.
Nice to yes, I was curious about this because we are working on something that is not exactly this one, but somehow